The integral test is kind of like this microscope here. When we first got this microscope, we got it kind of on a whim. It was like, hey, that's kind of neat. I wonder if we'll find a use for it now and again. As it turns out, we use it all the time. Now that we've got it in hand, we know how to use it, it gets used for all sorts of things. Fixing things big, fixing things small. You'd say, how would I fix something big? Well, you figure it out. The integral test is kind of like that. At first it's like, hey, this is a neat test for convergence for a series. And then pretty soon it's like, wow, this is the test for finding if a series converges or not. It's the go-to. So let's see how it works. The integral test says if I have a function, f, that is positive and monotonic decreasing, then the series, whose terms are given by fn, converges if and only if the integral with the same function converges, and that integral goes from 1 to infinity. Now, the if and only if is a pretty strong condition. That means that if the interval converges, the series does. If the series converges, the integral does. If the integral doesn't, then the series doesn't, etc. It does not tell you the value of the series. So, as a caution, this does not compute the value of either. You'll have to find those yourself if you want them. But it's pretty handy. Now, you might ask, why does this work? And the reason why this works is because actually the series is actually both a left and a right Riemann sum for the integral, depending on whether you use or you skip the first point. So the picture is really the beginning and the end of the story. So if you draw the function is positive and decreasing. And if here is 1, my series really is taking rectangles at the integer points. You can see right away that if I take my sum, like so, the sum of rectangles is the series from n equals 1 to infinity of fn. On the same kind of idea, this area here is the integral. So the area here is the integral from 1 to infinity of fn, well, fx perhaps. Now, if I were to want, this has given me a left sum. If I wanted a right sum, let me do that in red. The right sum, well, you should notice, actually, the right sum is really just the same sum as the left sum, except that I've skipped the first rectangle. Because in particular, if I get rid of that, yeah, you can see that this rectangle has moved over to here, this rectangle has moved over to here, this rectangle has moved over to there. So these rectangles is equal to n equals 2 to infinity. So you just leave off the first. Of course, these two series, both the one that I've marked in red and the one I've marked in black, converge exactly the same. The first few terms don't change the convergence at all. So basically the integral is both an upper and a lower bound for the sum, although there's some error, so that's why it doesn't compute the actual value. Now, why can this be useful? Well, the reason why this can be useful is because there are crazy lots of sums out there, lots of series, like this one. This series, it's got a crazy sum that involves pi's and such. You wouldn't know that just by looking at it, but you can tell that it converges using the integral test. So for the integral test, we take this sum, we say, I want to know if it converges or not. So let's instead write it as an integral. And conveniently, the fancy and convenient thing about the integral test is that we know antiderivatives. The antiderivative for this is minus 1 over n, which is to say this is the limit as n goes to infinity of 1 over n minus 1. And you will notice the limit as n goes to infinity of 1 over n is 0, so 1 converges. Therefore, so the caution here is the integral has got value 1. The series does not have the value 1. It involves some awful things with pi. It took Euler to figure out what the right answer was for that sum. By some very clever reasoning, in fact. So, point of the matter is the integral test does not tell you the value, but it does tell you, hey, it converges. On the other hand, what about the harmonic series? We already know the harmonic series diverges. So this means the integral is also going to diverge. That's what the integral test tells us. And actually we can check that because actually finding the antiderivative for this is not so hard. It's a natural log. And the natural log of infinity is indeed infinity. So, yep, that works out. It's worth noting, people like to play with sums of this form and call them something specific. This is called, if I take 1 over n to the p, I call that a p series. And all the p series have the nice property that all the different p's, we can use the integral test to check their convergence. And in particular, if p is greater than 1, strictly greater than 1, not equal to 1, then a p series converges. Pretty handy, and it comes out of the integral test. But you'll find many, many, many other uses of the integral test as well. It just keeps coming up over and over again because series are actually kind of hard to find out whether they converge or not. But integrals, since we know what antiderivatives are, and we can find some antiderivatives now, then we can use that to find out if an integral converges, and so therefore find out if the series converges. So, add the integral test to your toolbox. You'll find it's a tool you keep coming back to.
Hey, since you got that thing out, I've got a question for you. Can you help me get this splinter out?
Oh, no problem.